Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching KCET 60 out of 60 in physics series, where I am trying to help you to achieve 60 marks out of 60 in your upcoming 2025 KCET exam. So if you are following me from the beginning, then I can definitely guarantee that you will be very close to achieve that 60 out of 60 targets. We are at the last chapter of your second PU, but it is last, but as we say, last but not the least. Okay, this is a very important chapter. 4 questions usually comes from this chapter on an average, and it can go up as much as 5 questions some years, and some years it can be 6 questions as well. But on an average 4 question comes from this chapter. So this is a very important chapter, but there is a asterisk marks because this chapter used to contain some concepts from digital electronics. That part is now deleted, so no digital electronics related questions will come for 2025. So there are some few questions from digital electronics in 2024 exam which were later decided to be deleted because they are out of syllabus. So if you are wondering, I have to study digital electronics which is not there in our book, no, you don't have to study digital electronics, but this is a big chapter, a completely new type of concept. So I have decided to divide this chapter into 3 parts. Today will be the part 1, where we will discuss about conductors and semiconductors in different way. Okay, there are 2 different way to define a conductor and semiconductor. Also in between insulators will come, but mainly conductor and semiconductors are important. Insulators are not so important unless and until you are studying the chapter capacitance. So you have to be careful, and for a weekend test program and the note of this lecture, if you are not yet downloaded the WhatsApp and joined our WhatsApp group, you have to join our WhatsApp brigade so that you can get the update as soon as we are posting a new video, as soon as we are uploading the question paper for your weekend KPL program, which is completely free of cost. Only cost is that you have to join our WhatsApp group. Okay, so that is the only thing that you have to do. And for rest of you, let me start with the discussion of this chapter. The content of this chapter will be based on, first of all, semiconductors and conductors in terms of conductivity, in terms of resistivity, which is important. Previous year questions, we will see that they have asked question based on conductivity and resistivity of materials. Next, we will learn completely new thing is called band theory. Okay, band theory, band energy, everything we will learn in this lecture. Then we will learn how to define a conductor based on band theory, how to define an insulator based on band theory, and obviously how to define semiconductor based on band theory. And we will conclude today's lecture from on band theory, and we will start with different semiconductors from our lectures on tomorrow. Right, so let's start without any delay that what is conductors and semiconductors. So far we have learned that there is something called conductivity, right? If you remember, we started the discussion with the term called resistivity. So R equals to resistance, R equals to rho L by A. Right, if you remember, this was the relationship that we have learned in the chapter current electricity, and we said this is resistance and this is called resistivity, and resistivity varies from material to material, but for metals, for conductors it is usually very low, for non-metals this is very high. And also we have learned that there is another thing called conductivity, which is denoted by the symbol sigma, and this is nothing but 1 by rho. Right, these are all we have learned. Okay, the unit for resistivity is ohm per meter, and ohm meter is the unit of resistivity, whereas unit of conductivity is ohm inverse meter inverse. Right, now also we learned that J is equal to sigma E, another form of Ohm's law. Right, that was also there, J equals to sigma E, if you remember. So this is nothing but current density in terms of electric field, and sigma here is the conductivity. These are all the known equation that we have learned in our previous chapters. Now we will define conductors insulators and semiconductor based on this conductivity and resistivity thing. Okay, so conductivity is denoted by sigma and resistivity is 1 by rho, that is rho is resistivity, sigma is conductivity. Okay, so these are the basic things that we need to remember. Now metals and conductors, they usually have very low resistance, right? Low resistance means low resistivity, low resistivity means high conductivity, right? So basically these are all connected using a thread, right? High resistivity means low conductivity, low resistivity means high conductivity. So they are conductors are very good conductor of electricity. Okay, not everyone, but on an average all the metals are good conductors. There are certain non-metals which are also good conductors. For example, graphite is a good conductor, right? Gas carbon, it is also a good conductor. There are a few examples of non-metals having good conductivity, but usually metals are good conductors and they have low resistivity and high conductivity, right? Now what is the range of their resistivity and conductivity? So their resistivity varies from 10 to the power of minus 2 to 10 to the power of minus 8 ohm meter, right? This is the usual range. Okay, for some metals it may be even lower, some metals it even may be higher. Okay, but usually it varies from 10 to the power of 2 to 10 to the power of minus 8. So 10 to the power of minus 8 means very good conductor. Okay, 10 to the power of minus 2 means okay conductor. Okay, but it is still a conductor. And as you can see, the corresponding conductivity is 10 to the power of 2 to 10 to the power of 8, obviously 1 by rho, right? So conductivity, higher conductivity means good conductor, lower conductivity means weak conductor, not so good conductor, right? So this is the basic definition of conductors in terms of conductivity and resistivity. Resistivity means how much resistance it offers in unit length, right? Now let us go into the new type of material which is called semiconductors. Okay, now we are defining in terms of actual values, that is conductivity and resistivity. Previously we said semiconductors are something which is in between conductor and insulator, which I said is not 100% correct. So now we are talking in terms of some real values. What are the values? So conductivity, resistivity of a semiconductor varies from 10 to the power of minus 5 to 10 to the power of 6. So the range is very high. You can see that it is minus 2 to minus 8. Here it is minus 5 to plus 6. Okay, so minus 5 means very good conductor to 10 to the power of 6 ohm meter. That is almost the borderline insulator, right? And its conductivity varies from 10 to the power of 5 to 10 to the power of minus 6, right? So as I said, it is almost a very good conductor till borderline insulator, right? So that is why they are called semiconductors. Okay, they are not usually conductors, but under certain condition, under certain circumstances, you can convert them into conductors. Okay, and one more important thing is that you can control the flow of electron. Okay, in conductors you apply potential, the electrons will go automatically. You cannot control that flow in a conductor, but in a semiconductor, by varying something, you can control how much current is flowing through that conductor. That is why semiconductors are not so easy. They have certain properties, and sometimes they behave as insulators, sometimes they behave as conductor. That is why they are very interesting. We will see that throughout the chapter. Once the chapter is completed, I hope all of your doubts, all of your questions will be cleared. But so far you should know that semiconductors are something which are in between insulators and conductors. Okay, now let's talk about insulators. Insulators are very high resistivity and low conductivity, right? So what is the range of insulator resistivity is of the 10 to the power of 11. So very high resistivity, and its resistivity goes till 10 to the power of 19. So very high resistivity. Okay, and its corresponding conductivity is 10 to the power of minus 19, minus 11 to 10 to the power of minus 19 ohm inverse, meter inverse. Now ohm inverse, sometimes you will see that there is another unit for ohm inverse, okay, that is called Siemens, okay, and it is denoted by S, but S is not any new unit, it is just ohm inverse. So that's why I am using ohm inverse unit. So I don't want to trouble you using the unit Siemens. Siemens is nothing but ohm inverse, okay. Now, the values of rho and sigma given above are indicative of magnitude and could well go outside the ranges, okay. So as I said, this is just to give you an idea that how the conductivity varies, how the resistivity varies for different materials, but based on materials, some materials may be good, maybe very high resistivity, from that 10 to the power of 19 as well, and in some cases the conductivity of insulators can also be slightly lower than whatever range is given. So this is just to indicate that what may be the range of conductivity, what may be the range of resistivity, right. Now we'll go outside the ranges as well. Relative values of the resistivity are not the only criteria for distinguishing the metals, insulators and semiconductors from each other. So there are different ways to distinguish between conductor, semiconductor and insulator. This is not the only way. So only if I say, okay, this is the conductivity, this has to be a semiconductor, not always, but okay, this is one way. There are different ways and there are different theories. We will discuss about one more theory which is more appropriate to understand what is happening inside the actual atom. So that's why we will discuss that as well. Now there are a few types of semiconductors. So because we have started the chapter semiconductors, so we have to learn about different types of semiconductors. So first of all, there are elemental semiconductors, which are basically meaning that they are elements, simple elements without any compounds, simple elements like hydrogen, like oxygen, like nitrogen. So there are two elemental semiconductors. One is silicon and another is germanium. Okay, silicon is basically, if you see sand is basically a compound of silicon. Okay, silicon on earth, surface of the earth, the most abundant material is silicon. It is available very commonly. You can see, you can take the soil, it also contains silicon. Silicon is everywhere. Silicon and germanium are two types of semiconductors. Okay, now compound semiconductor, there are few compounds, elements are only two. Okay, compounds, you can synthesis multiple different types of compound to form semiconductors. So now inorganic semiconductors, so these are only using inorganic samples, inorganic material. I hope you have learned about inorganic and organic in your chemistry. So inorganic samples, for example, cadmium sulfide, gallium arsenide, okay, cadmium selenide, okay, INP. So they are basically indium phosphate. They are basically examples of inorganic semiconductors. They are also widely used in different applications. Okay, and organic semiconductors, for example, anthracene, doped phthalocyananes, okay, they are the examples of organic semiconductors. But organic polymer semiconductors are also very popular. Okay, organic polymers, the polymer, you know that simple organic molecule, when the chain is very long, then we call it polymers. So organic polymers are also very common. Polypropylrole, okay, polyaniline, okay, polytryptophan, they are also examples of organic semiconductors. Organic semiconductors are very interesting semiconductors based on different properties. I will discuss about that in a later part, okay, if possible. Most used semiconductor devices are based on elemental semiconductors, silicon or germanium, and compound inorganic semiconductors, right. So most commonly used, whatever we use in our day-to-day life, mostly all electronic devices are basically based on either elemental or compound. But nowadays organic semiconductors are also coming to be very, very popular. One of such example is you may have heard the term OLED, okay, OLED or OLED or AMOLED. Okay, if you are a gadget freak, you may have heard your mobile has a AMOLED display, your TV has OLED display. So what is this O stands for in that OLED or AMOLED display? Okay, AMOLED means active matrix organic LED, okay, and OLED means organic LED. So O stands for organic, and LED is a type of basically based on semiconductor principle. We will discuss about this in our future lectures. But AMOLED and OLED are basically semiconductors based on organics compound. Okay, so organic compounds, especially organic polymers, are coming to be very useful in our future, and in future even maybe we will use computers based on organic semiconductors. Okay, so far organic semiconductors are only used in displays, mainly in displays. Okay, computer display, mobile display, camera display, etc. But they might find their uses inside the CPUs, inside the hard drive very soon. We don't know, right? Now let us see one question from KCET 2022. The resistivity of a semiconductor at room temperature is in between. So at room temperature, what is the resistivity of the semiconductor? So we have learned the semiconductor, if you remember, it is between 10 to the power of minus 5 to 10 to the power of 6. Right, 10 to the power of minus 5 to 10 to the power of plus 6. Okay, so from there you can see that in this given options, okay, 10 to the power of, so in that expression we learned that the resistivity of a semiconductor is 10 to the power of minus 5 to 10 to the power of 6 ohm meter, right? So ohm meter is the average resistivity of semiconductor. Now if you convert it into ohm centimeter, then what you have to do, you have to add plus 2, right? Meter is 10 to the power of 2 centimeter, so it will be from 10 to the power of minus 3 till 10 to the power of 8 ohm centimeter. Okay, so if you remember the data, then you can answer the question. Don't get confused. It should be between 10 to the power of minus 3 to 10 to the power of 8 ohm centimeter. Okay, because they have changed the unit, so you will not be able to answer it directly. You will be confused. Okay, whether B is correct or D is correct. Definitely these two are not correct, because this is an insulator, this is an insulator. Now what about this? This may be insulator, this may be semiconductor, but actual range is from 10 to the power of minus 5 to 10 to the power of 6. So whatever option is as close as possible from the actual value, that will be your answer. And in this case, as you can see, it is exactly matching with the data that we have learned. So KCET 2022, if you have studied this question, you will be able to score 1 marks. Okay, if this kind of question comes in your 2025 exam, you will score 1 mark, right? Now let's look into a completely new thing called band theory. Okay, band theory is very interesting. So let's start the journey. According to Bohr's atomic model, so we have learned Bohr atomic model. What is Bohr atomic model? There was a nucleus, positively charged nucleus, and electrons are orbiting around it. Okay, so in an isolated atom, the energy of its electrons is decided by the orbit in which it revolves, right? So angular momentum is fixed, nh by 2 pi. Now higher the orbit, angular momentum will be higher, because h by 2 pi is constant. So more higher the quantum number, higher will be angular momentum. Similarly, energy will be higher, right? At lowest ground state, the energy is lowest, and as it goes up, energy becomes less and less. It becomes less and less negative. That means energy is higher and higher, right? So but when the atoms come together to form a solid, now this is for a single atom. Okay, now inside a suppose I take this pen. This pen has multiple atoms inside it, right? So if I consider this pen, then it is not a single atom. There are multiple atoms, and they are very close to each other. Okay, they are very close to each other, because most part of the atoms are empty. So we know that all the atoms are packing up close to each other, so, and they are forming something called a crystal. Okay, that is what we are calling a crystal. Now inside a solid, they are close to each other, so the outer orbits of electrons from neighboring atoms would come very close to each other. So suppose one electron is orbiting here, one electron is orbiting here, another electron is orbiting here. So they are on top of each other, and they are separated by a very small distances, so they will overlap. all the outer electrons, outer shell electrons are very important. They are called what? They are called valence electrons. If you remember in chemistry, we learned that the outermost electrons, they take part in the chemical reaction, and that's why they are called valence electrons. So these valence electrons, valence shells, they will overlap, they will merge with one another, and the electrons, they are staying in that region. They will sometimes forget the sense of which atom actually it belongs to, even though it has a particular atom associated with it, but these electrons can easily jump from one atom to another atom, and the other electron atom can also jump from this his own atom to a new atom. So they can exchange places, they can move around in that space, okay, in that area. Okay, so instead of having a small rubber band kind of structure, it has a very thick kind of elastic band. You can say that like a band, right? Friendship band. Okay, so initially when you are considering a single atom, the orbits are like a single rubber band. Okay, and when they are sitting inside a crystal, sitting inside a metal, a solid, then they behave like a thick plate of rubber band, which is very similar to your friendship band. If you are exchanging a friendship band during friendship day, that was in August, so that thick band is called a band. Okay, and they are having same energy. All the average energy of the all electrons are same. Okay, all the electrons in the average, they may be vary from one atom to another atom. Very important point is individual electron energy inside a single atom is different, but when they are inside a solid, all electrons in the valence shell, they share a common energy, and that is called the band energy of that particular band. Understood? Very important. Okay, they would make the nature of electron motion in a solid very different from that of isolated atom. So electrons move in a complex way rather than in an isolated atom, and it is very difficult for us to observe using isolated atoms. We consider multiple atoms every day. We encounter solids, like we even starting from our day, starting from when you take a pen, you start writing, they are all multiple atoms are sitting together. So you hardly encounter single atom. Okay, even air particles that you observe are not single atom, they are compound most of the cases, or at least they are consisting of more than one atom. Okay, so air is the closest thing that maybe have a single atom possible in some sense, but otherwise all the solid that we observe are having consisting of multiple atoms. That's why this band theory is very, very important to understand the properties of solids, and it is only applicable to solids. Liquid and gases, they don't have this band theory, so that is complicated for liquid and gases. I will not going to discuss that, but for solids it is very, very important to learn about band theory. Inside the crystal, so crystal is the solid. When all the atoms are sitting together having dinner, they are discussing amongst themselves, so they are called crystal. Okay, crystal is like your family dinner. When everyone from the family comes together having a dinner together in your home and sitting, everyone has a fixed place. So your grandfather is sitting on the corner, your father is sitting on the other corner, like that. So whatever the arrangement that is there, so that is called a crystal. Okay, everyone has a fixed place. Each electron has a unique position. Okay, and no two electrons see exactly the same pattern of the surrounding charges. Because of this, each electron will have a different energy level. These different energy levels with continuous energy variation from what is called energy band. So individually one electron is varying in energy. Okay, individually, suppose I have 1.1 eV, another one has 9 eV, 0.9 eV, another one has 1 eV. So each of the electrons have different energy, but when they sit together, their average energy is constant. Okay, this is very important. Average energy of the all electrons is constant, and that is not changing with time. Okay, even though all the electrons having different energy, all the average energy is constant, and that level of energy is called a band, right? Now the energy band which includes the energy levels of the valence electrons is called the valence band. So the band where all the valence electron stays. Okay, so you can consider this to be a train where all the persons sitting in the lower compartment, lower section, okay, lower berths, they are having some energy. Someone is sitting in the middle berth, they have some energy, and someone sitting in the top berth, they having same energy, right? So valence electrons are those which are residing on the outermost shell. We are not interested any electrons which are residing inside. They may be of interest in chemistry, but in physics we are only concerned about valence electrons, okay, whatever electrons which are residing on the outermost shell and they have some energy, they are sharing some space between them, and that is called the valence shell, okay, and valence band, okay. So valence electrons is called the valence band. The energy band above the valence band is called conduction band, the empty shell. So we know that an atom has multiple shells. For example, hydrogen has multiple shells, but only at ground state only one of them is occupied, right? That n equals to 1 shell is occupied, but they have K, L, M, N, O, P, there are multiple shells, okay. We are not going into orbitals, only orbit is sufficient for physics, okay. So so as I am saying that only valence shell, they are all staying together. So all the valence shell, they are having the same level. I am saying that this is valence band, okay. And the empty shell above the valence band is now we are calling it as conduction band, okay. If some electrons move from valence band to conduction band, something new will happen. We'll discuss that in a while, but that is called conduction band. Conduction band is like the empty floor above you, okay, and the floor that where you all are staying is the valence band, okay. So if you are staying suppose in a one-storied building and the rooftop is now conduction band and your floor where everyone is staying is the valence band, okay. Now the gap between the top of the valence band and the bottom of the conduction band is called the energy band gap or forbidden energy gap, okay. So all the electrons having a small variation of energy is staying in this band, okay. See, this is the band for all the valence. So these are all different valence orbits, they are overlapping with each other, okay, and they have different energies. So this is called valence band and we generally denote it by VB. Valence band is denoted by VB, okay. And there is a conduction band which is empty. In general, the gap between this point and this point is called the energy gap, energy band gap or forbidden energy gap. Everything is same. Forbidden energy gap, band gap, they are one or the same, okay. This gap between the top of the valence band and bottom of the conduction band, okay, they have some variation, okay. It may be large, it may be small, it may be zero depending upon the material, okay. We will discuss each case individually. This gap can be zero for certain material, this gap can be very large, this gap can be very small as well depending upon what type of material we are discussing. So mostly all the electrons are staying here, okay. And if we can take some electron from valence band to conduction band, something new will happen. That is very interesting, that we are going to discuss in this lecture. The energy band which includes the energy levels of the valence electron is called the valence band. The energy band above the valence band is called the conduction band, okay. Now let's move on. First case number 1, the conduction band and valence band overlap. So conduction band and valence band, they are overlapping. So as you can see, this is the conduction band, okay, and this is the valence band and they have a common intersection. So they are overlapping with each other. Now what will happen? If they overlap, what will happen? When there is a overlap, electrons from valence band can easily move into the conduction band. So if so basically what that means is that valence band can easily electrons here, electrons are always staying in valence band, so they will say I can go to conduction band. So basically it is like your neighbors and you have a balcony and you can jump from one balcony to another balcony. Okay, if the gap is very high, that is forbidden energy gap, you cannot jump, you will fall. But if the balconies are overlapping, you don't need to jump, you can easily walk from your home to your neighbor's home. Okay, for just for fun. Now electrons from valence band can easily move into the conduction band. This situation makes a large number of electrons available for electrical conduction. Okay, when the valence band is partially empty, so a valence band is not completely full, it has some scope of accepting electron from outside. Okay, electrons from lower energy level, okay, that I said I am not interested upon so much, but in some cases it is important as well. If the valence band is not full, okay, so they can still take some electrons. What happens in that case? Some electrons from the lower energy level, they can still comes to the valence band. Okay, so electrons from its lower level can move to the higher level by making conduction possible. So electron valence band is empty, valence band has some space to accommodate electrons, so lower energy level electrons are coming and then they are moving to conduction band, and when the electron is in conduction band, it can conduct electricity. Why conduction band is important? Because an electron staying in conduction band, if you apply an electric field, it will move in the opposite direction of the electric field. That is, it can carry current. To carry current, electrons must be present in the conduction band. If there is no current present inside the conduction band, then it will not be able to carry current. So if you remember in the chapter of current electricity, I said a metal or a conductor is a sea of electron. What is the meaning of that? That means the electrons are available in the conduction band. There are ample amount of electrons are available in the conduction band. These electrons can carry electricity. Okay, so to carry electricity, electrons having electrons in the valence band is not sufficient. Electrons must be present in the conduction band. If electrons are present in conduction band, then this material can carry electricity without any restriction. Okay, higher the conductivity, more amount of electrons are available to carry current. Lower the conductivity, less amount of electrons are available to carry the current. Clear? Now, when the valence band is partially empty, electrons from its lower level can move to the higher level by making conduction possible. Therefore, the resistance of such materials is low or the conductivity is high. Okay, such materials are called conductors. So conductors are basically the materials which have a overlapping of conduction and valence band. Now tell me, what is the energy gap in this case? Forbidden energy gap. Forbidden energy gap in this case is 0. So forbidden energy gap is 0 for conductors. So if you are talking about conductors, electron can move freely from valence band to conduction band. So forbidden energy gap or band gap is 0 for conductors. Very important point to remember. Now, in a good conductor, this is also from one of your previous year questions. In a good conductor, the energy gap between the conduction band and the valence band is, what I said? Infinite? No. Wide? No. Narrow? Maybe, but not 100% correct. Then it should be 0. Okay, even narrow is not an option. Okay, it should be 0. For a good conductor, the energy gap between valence band and conduction band should be 0. There is no other option. Okay, it should be 0. If it is a good conductor, the energy gap should be 0. Now let us look into another case, case number 2. In this case, the band gap is high and it is higher than a particular value of 3 electron volts. Okay, 3 electron volts. Okay, we will see why it is important. So the band gap is very, very high. Okay, so I gave you the example where your neighbors and your balconies are touching. So if they are touching, they are overlapping, that means you can move without doing anything. But if the gap is very high, if you jump, what will happen? You will fall and you will die, right? Or you will break your legs. So don't try it if the gap is too high. But if the gap is very high, you will not be able to reach to your neighbor's balcony. right? There are no electrons in the conduction band and therefore no electrical conduction is possible. Note that the energy gap is so large that the electrons cannot be excited from the valence band to the conduction band by thermal excitation. Even if you are heating this material, okay, thermal excitation means when you heat material, okay, electrons gain energy, and because of that energy, electron might go from valence band to conduction band, right? But that is also not possible for insulators. Okay, electrons will not be able to reach to the valence band. Even before reaching the valence band, the material will melt. Material melt means there will be no longer conduction band, no longer valence band, and you will not be able to make it a conductor. This is the case of insulators. So if the energy gap, if the band gap is more than 3 electron volts, then that is a insulator, that is an insulator. Okay, you have to remember that band gap value for conductor is 0. It is greater than 3 electron volt for insulator. Now what will happen if the band gap is less than 3 electron volt? Obviously, next question. So we have put our emphasis on that 3 electron volt. So if it is more than 3 electron volt, it is an insulator. If it is less than 3 electron volt, that means your neighbor's house and your house balconies are close to each other, not exactly touching, but if you jump from your home to your neighbor's home, then you can reach there. Okay, so there is a possibility that you will reach to your neighbor's home. Okay, so because of the small band gap at room temperature, some electrons from the valence band can acquire enough energy to cross the energy gap and enter the conduction band. So if the electrons staying here at room temperature, remember that at room temperature at absolute zero, it might still behave as a insulator. Okay, so at absolute zero, it is not possible for an electron to go from, normally it is not possible for an electron to jump from valence band to conduction band. Absolute zero means, yes, that minus 273 degree Celsius. So at that temperature, it is difficult for an electron to jump from valence band to conduction band. There are different ways, but normally it is not possible. Okay, and normal room temperature, electrons can easily jump from valence band to conduction band easily. Okay, and because of the low band gap, electrons sometimes slip into the conduction band, and these electrons can carry current. Okay, now if you can control how much electron is moving from valence band to conduction band, you can even control the amount of current as well. That is what we are looking for, right? Now these electrons, though small in numbers, can move in the conductor band. Hence the resistance of the semiconductors is not as high as that of the insulator. So they are basically called semiconductors. In semiconductors, the forbidden energy gap is less than 3 electron volt. Okay, this 3 electron volt is very important. If the forbidden energy gap is less than 3 electron volt, then it will be a semiconductor. If it is greater than 3 electron volt, it will be an insulator. Okay, so it is like a passing mark. So if you remember, your passing mark in your exam is 30%. Okay, if you score 30%, you will pass. If you even score 29, you will fail, right? Even 1 mark matters. So similarly here also 3 electron volt is the passing marks for semiconductor or insulator. If you are greater than 3 electron volt, then you will be an insulator. If you are less than 3 electron volts, you are a semiconductor. Okay, semiconductor can behave as an insulator as well as conductor based on the temperature, right? Now let's look into the homework question. So this will be the last topic of today's lecture. It is a brief lecture, not super long. So I hope you have enjoyed it. New concept, any doubts, any questions, if you have, don't forget to mention that in the comment below. I will definitely look into it and I will reply to that. Okay, so this is the first question, very interesting question. The forbidden energy gap for germanium crystal at 0 Kelvin. What is 0 Kelvin? 0 Kelvin is absolute zero. Okay, do some research, try to find out the value and mention the answer in the comment below. Okay, this is from your previous year question. Now next question, the energy gap in case of which of the following is less than 3 electron volt but greater than 0. this is also from your previous year question. Okay, this kind of question also comes. That's why I am trying to put more emphasis on this part, because you don't know from which line, which a concept they will going to ask questions, because one important concept, one question from where every year at least 1 or 2 questions, up to 2 questions is to come, is no longer part of the syllabus. So they will ask questions in depth, in detail, and band theory and band energy is very important concept. From there I expect at least 1 question will come in KCET 2025. So this is a very important question. Try to answer this question and mention the answer in the comment below, and all the videos that we are doing is getting uploaded in this playlist for physics. Okay, KCET 2025 physics playlist, you have to bookmark it. Whenever we are uploading one video, one new lecture, you can access that from this playlist. Also it includes the KPL series, so KPL series is also included here, so don't forget to bookmark this series. And whatever your doubts you have, you can post that questions in your latest video. I do not take comments from previous videos unless it is tagged. So try to post whatever question. Suppose you are studying video number 1 and you are thinking, okay, what the questions that I have some doubts, so ask that question in the latest video. Okay, I will try to answer from video number 1 as well. Okay, so don't worry, if you have any doubts, post the question in the latest video. Try to post the questions in the latest video. I will try to answer. Okay, and then to participate in KPL, you have to join our WhatsApp channel. The link is given in the description. And if you like the video, don't forget to give it a like and share and subscribe to our channel. I will be back with semiconductor part 2 tomorrow. Till then, bye bye.